So what do we got going today?
Today I want to start with the graphing absolute value of inequalities.
Okay.
And then I guess we could take it from there.
Okay.
So,
You have a problem?
actually, no. He didn't give us any problems on this.
Well, let me make one up.
Okay.
First of all, if I say, let me think for a minute how I'm going to make one up here. You want to graph, well, let's just take this for starters.
Okay.
Okay. What this means is that y equals two things. Y equals x whenever x is greater than 0, and y equals minus x whenever x is less than 0. This is a little different than what we ended with the other day, because we weren't talking about graphing that.
Right.
In other words, we were talking about solving inequalities. Well, this is an absolute value function, and when y is equal to x, it looks like that, just has a slope of 1. And when y is equal to minus x, it looks like that, has a slope of negative 1.
Okay.
Okay? So the graphs of absolute value functions generally have this corner in them.
Right.
Okay? Now, let's say that I add a 2 to that. That is, have you had translations yet?
No.
Vertical translations, in other words, when I add a number to a function at the end of it, it's a vertical shift. It causes this thing to look like, instead of the cusp or corner being at 0, it's right there. Still has a slope like that.
Okay.
In other words, it would take your original function and just move it up 2.
Okay. And that's if you add it to the x, add it to the absolute value, like, or if it's outside the absolute value.
I'm going to go through each of those. Yeah.
Okay.
In other words, here, let's classify these, because it turns out that f of x notation is far more valuable.
Okay.
Because what did we do? In other words, if, let me go back here. If f of x was equal to the absolute value of x, and we ended up with absolute value of x plus 2, then that has to be f of x plus 2.
Okay.
That's called a vertical translation.
All right.
Not changing the shape of the function, is all I'm doing it is moving it up or down.
And you can do that freely?
With any function.
Okay.
If I, even a quadratic, if I say y equal x squared, that's this quadratic. But if I say y equal x squared plus 2, that's this quadratic.
And does that apply when it's like x squared plus x plus 2? Would it still always be up 2?
No.
From 0?
That's a little different. That's
okay.
a little different. That's the constant of a quadratic, whereas this is an alteration of the original. This is called the parent function.
Okay.
This is called a vertical shift.
Okay.
Now, let me move everything down a little bit because I want to be able to write these in order. This is an important part of Algebra 2, and you're going to need to know this if you haven't covered it. Maybe this is not what you want to spend your time on today, I'm not sure, but let me just give you a couple of other things. If I wanted to know what this was, that's a little different than what's above. This turns out to be the absolute value of x plus 2, right? In other words, whenever I put something in the parentheses that's not x, I'm going to evaluate the original function, and wherever I run across x, I'm going to put x plus 2.
Okay.
Okay? Well, it turns out that this x plus 2 is a horizontal translation. In other words, if I were graphing just the x plus 2, it would be my original absolute value function moved 2 units to the left.
Because it's where where that absolute value equals 0, right?
Yeah, in other words, yeah, here I'm graphing just this. I'm going to confuse you with all of these things here. Let's just take these one at a time. In other words, if the parent function is absolute value of x, and I say, well, what does this look like? I'm just going to substitute x plus 2 wherever I see x.
Okay.
And that has the effect of a horizontal translation.
Okay.
2 units to the left. Had I said x minus 2, it would be 2 units to the right.
How does that help you, though? When would you use that?
For graphing functions, what if I gave you a function that was like this? How would you graph that? In other words, there are all of these adjustments being made. They're called translations or reflections to the original parent function. I know how to graph this. Well, the way I figure out how to graph the one I just wrote is it's the absolute value function shifted 1 unit right and 3 units up. So its vertex is going to be right there. Okay, so if it didn't have that 2 in front, that's what it would look like. The 2 in front acts as a vertical stretch factor, making this thing steeper. In other words, essentially that's a slope of 2, and that's a slope of minus 2. So if I want to know how to graph that, the best way to do it is to really start from the parent function and figure out all 3 things that are going on.
Okay. So if you had... So how do you know, is the slope always being multiplied by the x? How do you know?
No, this 2 here can be talked about like this. In other words, when you see a function that is being multiplied by some constant, and that's what's going on here, you have the original function that's being multiplied by some multiplier, it acts as a vertical stretch factor. If I was dealing with a parabola that would look like that, then 2x squared would be steeper. It'd still be a parabola, but it would be steeper. If I said y equals 1/2 x squared, it's going to be flatter. In other words, when you have stretch factors, vertical stretch factors, they do change the shape of the curve.
Right.
But the way to think about them is this manner here. In other words, if I'm looking at a function, let's say I'm only doing one of these, well, if I want to know what 2f of x is, and f of x is this, then it's 2 that.
Okay.
Okay?
And
there's a different one, just let's cover these 4. If I have the multiplier inside, like that, that's a horizontal stretch factor. That would look like the absolute value of 2x instead of 2 times the absolute value of x.
So what would x be in that case?
Well, x can be anything. The domain of x is unrestricted.
Okay.
The key is when you are given a function that has been translated, it's much easier to graph if you can recognize what the translations are.
Right. all the different parts.
If I'm looking at this, I know that, well, starting from the middle, that should be a straight line. It's down. Starting from this part here, I know that my parent function was shifted 1 to the right.
Right, because it has to be a positive 1 to make it 0.
Correct. And that means it was shifted 3 units vertically up.
And if it was -3, it would be down.
Correct.
Okay.
And this means that
The slope
it's a
is
vertical stretch, where my point would have been lower, it's now twice as far away. So the effect is it makes it look steeper, and the reality is yes, the slope on this line is +2, the slope on that line is -2.
Can you give me another one of those that I could try and figure out?
Yeah, I was just going to say we can jump now into inequalities if you like.
Okay.
Before we do that, let's just cover that, because I know we may only have a half hour here.
No, we do have the full hour.
Okay. If I said f of x is greater than that, now we have what you were talking about in the beginning, which is inequalities combined with absolute values and figuring out how to graph them. Okay?
Okay.
First,
so do you use the same things you just used?
Exactly the same thing. In fact, my first step is going to be to see what that would look like if it was an equality. And it would look just like this. Okay?
Okay.
Now, second step is, should that be a solid line or a dotted line?
There's dotted lines?
There's dotted lines that cover greater than or less than. If it's greater than or equal, it would be a solid line.
Oh, we haven't learned that yet.
Covered that? Okay. Well, I can cover it real quick. So there's my dotted line representing the greater than, not greater than or equal to. Now the only thing left to do is to shade the region that represents where the function is greater than this.
Okay.
And what you look to here is the y-axis, or actually, technically, that is the f of x axis. That's the x-axis. Well, where is f of x greater than this function? It's...
Do you have to Oh, it's just inside?
It's inside. That's the only place where it's greater. If
it's less than, then it's outside.
Right. If I were to pick this point right there, that's clearly less than my function.
Okay.
It's a question of whether it's greater than or less than the function everywhere you're looking. In other words, if
we haven't done any of the shading
Well, okay. Well, I don't know if we're getting a little ahead of what you're about to cover, but it sounds like it. If your teacher told you that the next subject was going to be graphing inequalities.
Well, we learned graphing inequalities, but we learned it just with graphing I don't even know if that's still a parabola, but just graphing that.
Okay.
Instead of trying to find what's inside and what's outside.
Well, same thing applies, though. Let's say I said f of x is greater than x squared. First thing you're going to do is draw the parabola. Next thing you're going to do is realize that should have been a dotted line. Well, if I let's make it greater than or equal to x squared, and now its solid line is correct.
Okay.
Okay, that's the difference.
And it's greater than, so it's going to be inside the parabola.
Right, but it's not really correct to think inside or outside the parabola. The reason is the parabola goes to infinity. So eventually that parabola is going to go to the right as far as you want it to go. What's correct the way to think about it is any point that I pick going to be greater than the point on the curve? In other words, if I pick a point over here, that's greater than that curve. If I pick a point right there, that's less than that curve. If I pick a point down here, that's greater than that curve.
Okay.
Okay, now it is true that all my points that are inside the parabola are the ones that are greater. So it's not really wrong to think of it like that, but you won't always have parabolas that you're dealing with. Let's say I had a cubic function that looks like that. Okay, that's y equal x cubed and change. Well, now if I want to say f of x is greater than x cubed minus 2x plus 1. Let's say that's the function that I've drawn there.
Okay.
Well, now there's no inside or outside the parabola. There's only above or below the line.
And if it's greater than, it needs to be above the line. And
if it's less than, it needs to be below. The key on that is to only look to the y-axis. Unless, of course, the problem said x is greater than y minus 2 or something. And then, because the x is over here, then I'm looking to the x-axis. Let me make that function look like that. Well, now it's this whole area.
Okay. That whole area because it's...
Because I'm looking to the x-axis.
Oh, okay.
So
it's everything to the right of the line.
Yeah, to the right, exactly. It turns out in this case that appears to be the same as everything under the line.
Right.
But the key in all of these is to figure out which variable is on the one side of the greater or less than sign, and look to that axis to figure out whether we want to be either to the right. Usually you don't have an x over there. Most everything they're going to give you is going to be y, and the x will be on the right side.
Okay.
And that's why I always tell people to look to the y-axis. It's either below or above.
But if it's, so let's say they have f of x, that's like looking to the y-axis, basically.
F of x means the same as y.
Okay.
Okay?
When graphing?
Always.
Oh, really?
Yep. In other words, if I say that y equals x cubed minus 2, notice why this is better notation. Same thing. The difference is this tells me that I have a function of x. Y does not.
Right. So that tells you...
When I say I have a function of x, it means all the variables that are going to be on the other side are going to be x variables. I'm not going to run into any y variables. I'm not going to run into r variables.
So it's easier to solve.
Well, there's another advantage. I can now say, well, what is that function evaluated at 2?
Okay.
And what is it?
8 minus 2?
Correct. And okay, now let's go into calculus where I have to answer this question. What is that function evaluated at x plus h?
X plus h is
cubed minus 2. In other words, that's how I would write it.
Okay.
Okay. The lesson to learn is that no matter what is in the parentheses, no matter how complicated or simple it is, you merely take it and you substitute it for x, wherever you see x in the original function.
Okay, that makes sense.
So the f of x notation allows you to do all of these things that the y notation does not really do. I mean, sometimes you'll see them say, well, what is y of 2? In other words, they'll pretend they're using f of x notation, but not very often.
And y of 2, you would substitute x for 2.
I would substitute 2 for x, yes.
So whenever I see y equals
of 2 would be the same as f of 2.
Right. So if I see y equals x something, I can substitute for f of x?
Yes. And in fact, you can do it on the graph also. In other words, that's called the xy Cartesian plane, but it's perfectly acceptable to label your vertical axis f of x, and much more desirable in calculus.
All right.
I'll give you, well, just a 30-second reason why it's more desirable in calculus. If I want to find the area under a curve, which I have no way to do in geometry, but I can do it in calculus by splitting that up into a bunch of rectangles and adding up the area of all the rectangles. Well, if that's 1, 2, 3, 4, this point right here, the height of that rectangle is f of 1. The height of this rectangle is f of 2. This is f of 3, and so forth and so on. In other words, I don't know what f of x is yet even. Maybe this is some complicated formula. F of x equals, x to the 4th minus x squared plus 1 or something like that. So instead of figuring out the exact height of each rectangle, it's better to say that this point right here is f of 1. This point's f of 2, this point's f of 3, this point is f of 4.
That makes sense.
And so forth and so on. And then you can figure out the area. But anyway, this concept of calling it f of x or g of x or h of x is a vital one for moving into pre-calc and calc.
Okay.
Okay. Now,
so can we do a little bit more with the graphing the inequalities?
Yeah. Let's graph inequalities instead of absolute value inequalities for a moment.
Okay.
If I have f of x greater than 2x minus 3.
2x minus 3.
Just a linear equation.
So that means that my vertex is going to be minus 3 up.
Yeah.
I mean down. Well, minus 3 down.
Not the vertex. That's the y-intercept. That's okay.
Oh, okay.
Yeah, that's where you begin.
So the y-intercept is negative 3.
Correct. Mm-hmm.
And the x, we don't know the x.
What's the slope?
2.
Okay, so that's all we need is to go up 2 and to the right 1. That's the slope of 2. I now have 2 points. 2 points define a straight line.
So that's all I need.
Yeah. In this case, I got to use a dotted line because I made it greater than, not greater than or equal. And
right.
Because f of x is greater than this, which side of that line should I shade?
F of x is greater, so you're going to side the left side of the line.
Although I would rather you say the above the line.
Above the line, okay.
Okay. If this was x instead of f of x, then you would say it would be to the right of the line. But,
because f of x is the y-axis. Right, okay.
Right, f of x is the same as y. Remember that.
Right, so if
go ahead.
If f of x was x and it was less than, it would be to the left of the line.
Right. But like I said, I would even lose the whole concept of being left or right.
Right.
Because especially at this level, you're just not going to get functions that has x on the one side of the thing.
Yeah.
But if you did, it would be left or right. If it's y, then it's above or below.
Okay.
And this is y. So all we're going to do is we're going to go to the line, and we have to find a point above the line on the y-axis. So I'll find a point right there that tells me which side to shade.
Okay.
And that's the way you graph inequalities.
Okay.
All right. Now, adding absolute value to the equation doesn't change much.
So inequalities are always straight lines?
No. They don't
No?
have to be. No, let's put a parabola in there. In other words, if I have a quadratic,
Oh,
then it's a curved line. If I make it x squared, there's your curved line. Let's make it greater than or equal to x squared. So now I go to my y-axis. I find a point that's above the line. That's the inside is the place. Not the inside. Above the curve is what you want to shade.
okay.
And it can be x cubed. In other words, you can have different degree polynomials. And it's no matter what the curve looks like I said, when I had my curve that was more than a quadratic, and it looked something like this, if I'm saying f of x is greater than that curve, then it's got to be this area here.
Right. So, okay, so...
Now, throwing in the absolute value doesn't change much. Let's go back and look at that line. This line is, and here I'm going to use y notation. They're completely interchangeable.
Okay.
Okay. It's just shorter to write y. Now let's say y is equal to the absolute value of this.
Okay.
Well, the way to graph that is to merely go down to where it crosses the x-axis, and everything that's below the x-axis gets reflected.
Right. It's negative.
Well, it's now negative, but we know it's going to be positive. So I have to take this line and I have to reflect it over the x-axis so that it looks something like this. Now it has a slope of -2.
So you just you reflect it with the opposite slope.
Exactly. And I erase this bottom part.
But let's say it was y equals the absolute value of 2x and then -3.
Well, that's different.
Right.
In other words, that is graphing the absolute value of 2x and then shifting it down 3 units. That's
so
why these translations are pretty important to learn, is because it allows you to graph complicated slopes that would be tough to graph otherwise.
Right.
I mean,
so if
there's
that's
lots more I can do to this thing. Let's put some other stuff in here. I can have a negative sign, which means it's a reflection over the x-axis. I can have a stretch factor. That's a vertical stretch factor. I can have a horizontal stretch factor. I can subtract a number from that. And then I can have a vertical shift. So I can have a whole bunch of things doing. If I said graph that, it would be a little tough to graph without going back and seeing what the elementary function is. The elementary function is that. And each of these things, that's a reflection over the x-axis, that's a vertical stretch factor, that's a horizontal compression factor, that's a shift to the right by 4 units, and that's a shift up by 5 units. And there's only one other thing you can do, which is to put a negative sign in front of inside the function, and that's a reflection over the y-axis. So there's actually a total of 6 things that can be done to elementary functions.
Okay.
And those 6 things are 2 reflections, one over the x-axis, one over the y-axis, horizontal shift, vertical stretch, horizontal stretch. That's it.
Okay.
And
Go
ahead.
What the -3x, that part? Is that to do with the slope?
Now, here, let's take a simpler function and I'll show you what that does. Let me think for a moment. It is a reflection over the y-axis, which can't be shown with a parabola. Because if I reflect this parabola over the y-axis, what do I get?
The same parabola.
Right. So I don't want to use that to demonstrate a reflection. Let's use this function, which is y equal x cubed. Okay?
Okay.
If I reflect that over the x-axis, well, again, here, let me, for the sake of translations, label that f of x, because when you get the, if I want to know what f of minus x is, notice that's different than minus f of x.
Yeah.
This is a reflection over the y-axis. This is a reflection over the x-axis.
Okay.
Okay? So if I have the negative sign inside the parentheses, then this becomes negative x cubed, which becomes negative x cubed. Is all I have to see to how to graph that is to reflect over the y-axis. So this part here goes up to here, and this part here goes down to there. So my curve looks like that now.
Okay.
Okay? And again, this wasn't the greatest function to use because it turns out that minus f of x looks the same exact way. In other words, if I take that original curve and reflect it over the x-axis or the y-axis, it actually looks the same.
Right.
As it would, because negative f of x, which is the reflection over the x-axis, is just negative x squared. It's the same function. So it should look exactly.
Okay.
Okay.
So, all right. I want to work on this a little bit more, and then after this, I just need to clear up some things on graphing parabolas,
Okay.
like just regular parabolas.
Okay.
Sorry, one sec.
The only time, let me just say one last thing. If I had x greater than 1, and you might see it then, okay?
Okay.
How would I graph that?
X is greater than 1,
Yeah.
so the x-axis is greater than 1. So it starts from the point 1.
First of all, x equals 1 is a straight line. It's a vertical line. So there is the line x equal 1 going through the 1.
It's everything to the right of that line.
Correct. In other words, this is the one time where you may not see a y, is when you have vertical lines.
Okay.
Because vertical lines are described by x equals something. There's no y in a vertical line equation.
And same goes for horizontal lines.
That's y equal 4.
Okay.
Okay? So horizontal lines are y equals something, vertical lines are x equals something. Most every other kind of line is going to be y equals something.
Okay.
So if you run into this, and you might, then that's when you look right or left. And clearly that means that area right there.
Right.
And that's the only time you would look right or left. Okay.
So, let me see. Let's say f of x is greater than or equal to the absolute value of 2x plus 2.
2 inside the absolute value or out?
Out.
Okay. Where I'm going to start here is with the equality. So I'm really going to try to graph this thing because, first of all, it's a solid line. So if I start with the equality rather than the inequality, I'll get the graph.
Right.
And I just have to figure out whether to shade it above or below, right?
Okay.
Okay. So examining this, well, I see a couple of adjustments. I see that we've taken the elementary function, which is f of x equal absolute value of x, and multiplied the inside by 2. Well, that's the same as this. Okay. That's a horizontal compression. If my multiplier is inside my parentheses, that is a horizontal compression, as opposed to if that 2 was out there, that would be a vertical stretch.
Okay.
Okay? And you're right if you picked up on the fact that they're opposite. In other words, when the multiplier is outside the function, numbers greater than 1 are stretches. Numbers between 0 and 1 are compressions. Pi, come here. What are you barking at? Pi. Pi. Okay. In other words, if I had a parabola like that, and I want to say, well, 2x squared, that's outside the function. That's a vertical stretch. Makes that parabola look like that.
Okay.
Now, if I want to say, well, what if I had, that's f of x, and I want to know what f of 2x is, well, that's a little different. That is quantity 2x squared, which is now 4x squared. So a horizontal compression by a factor of this. So the result is you still, when you horizontally compress something, it's the same as a vertical stretch. Not the same magnitude, but the same adjustment. In other words, you make that parabola skinnier. All right, so if we look at what's happening here, I can see that this 2 is going to make my original function skinnier. So if
the slope is going to be 2, right?
Yes. Okay, so my original function, if I was just graphing the absolute value of 2x, it would look like that. Okay. Now I have to vertically adjust it by 2 without changing its shape. In other words, whenever you do a vertical shift or a horizontal shift, you do not change the shape of the curve at all.
You just move where it starts.
Move it left or right or up and down.
Right.
As opposed to stretch factors and shrink factors. In other words,
let's say the 2x, absolute value of 2x plus 2 all inside of the absolute value. Would that be a stretch factor?
It would be a stretch factor, but it would also be a horizontal shift. It would be both at the same time.
Let me look at that.
Okay. In other words, you're just suggesting that, right?
Yeah.
Okay, well, it's going to be this curve here shifted 2 units to the left. Same steep slope, slope of 2, but this is now at -2.
Oh. Okay, so it just moves horizontally when it's inside.
Right, exactly.
Oh, that's
I would write that as f of 2x plus 2.
Right.
So it's inside, both adjustments are inside the parentheses. That makes that a horizontal shift and that makes that a horizontal shrink.
So besides the coefficient of the x, what changes the actual shape of the parabola, or the...
Only vertical shifts or only vertical stretches or horizontal stretches. And, of course, going with the stretch is a shrink. If I multiply the whole equation by 1/2, that's a vertical shrink.
Right.
If I multiply the inside by 1/2, that is a horizontal stretch.
Okay. Okay, so if it's multiplied by the x, it's a stretch. If it's multiplied by the f of x, then it's a shrink?
Depends on whether the number is greater than 1. And they're the opposite.
Okay, no, that's not what I meant. I'm sorry.
They're the opposite.
If it's multiplied by the f of x, then it's a change in the y.
Right, at the stretch. Let's talk about multiplying by numbers greater than 1 or less than 1.
Okay.
Because it matters. In other words, if I multiply outside the function by a number greater than 1, that's a vertical stretch.
Right. Okay.
I multiply
vertical because f of x is y.
Correct. So every point's going to be 3 times further away from the x-axis, and that is the equivalent of a stretch.
So how do you compensate for that? How do you look at that stretch?
Change
exactly. Change the shape by what?
By that factor. In other words,
so the slope is going to be 3?
What the original function is. I don't want to make these really complicated because it makes it difficult to see.
Right.
If my original function, and you always come back to the original function.
Right.
Okay, the original function, which has slopes of 1 and -1, there's my original function. Well, if I had 3f of x, that's the same as 3 absolute value of x. Notice the 3 is outside the function.
Right.
And that's a vertical stretch by a factor of 3. And the way to remember it is that point, instead of being this far away from the x-axis, has to be 3 times further. Has to be up here. Well, when I look at it like that, I can see that every point has to be steeper. Same thing over here. And so I end up with, that's what a vertical stretch does.
Okay, so it takes your original, I don't know how to describe it. It takes your original function. Okay, so wait, let me try something. So let's say it was 3 times the absolute value of 2x. How would you do that? Because that changes it too.
That's correct. The 2 is then a horizontal compression factor.
Okay.
Okay. And in fact, if I wrote this, I can actually remove that 2 from the absolute value.
Why?
Because it's positive. Because it's a number that doesn't change. This is the same as that.
Oh, so you can multiply them?
Do multipliers and dividers, take them out, leave their sign the same.
So you make your slope 6 at that point.
Exactly. And notice that's what the effect would be. That makes it skinnier from a vertical stretch. That makes it skinnier still from a horizontal squeeze.
Right, because it's making it steeper.
Right. So I end up with a steeper slope based on both of them.
Okay.
But notice.
And so when you have absolute values, that's when you get that v because they're mirrored.
Yes.
But when you don't have absolute value, let's say it's just an inequality, will it just be a line?
Well, let me show you what absolute value looks like when it's not linear. In other words, so far we've looked at just linear. If I had a curve, in fact, let's take the sine curve. I know you haven't had trig, but you might be familiar with that curve. Okay?
Okay.
That's y equals sine x. Well, if I want to know what y equal absolute value of sine x is, I just take every point that's below the x-axis and reflect it over the x-axis. So that becomes that.
And
I erase the bottom part. So that's what that function would look like. Y equal absolute value of sine x. You just take everything below the x-axis and reflect it over the x-axis. Because it has to be positive, right? In other words, there's no value of x that y is going to be negative.
You can't have an absolute value that's negative.
Exactly.
Okay.
So it always has to be graphed above. Now, let me just change one thing here. Let's say I subtract 2 from that. Okay? Well, how do I graph that? I take this shape. That's a vertical
and move
shift.
It down 2.
Yes. I take that exact shape. I don't change it. I move it down 2. Starts right there. Ends up there. Looks something like that.
Okay. All right. I get that now. That's not that difficult at all.
No. And that's how you treat absolute value.
It's weird that you can make like 3 times the absolute value of 2x. It's weird that they multiply with each other because they're not like terms.
Correct.
Oh no, you can multiply like that.
The thing is that like I said, you can always, that's always equal to 3 times the absolute value of x. Because that's always a positive 3 when it's written like that.
But what if it's a negative? Even if it's a negative 3, it's still
negative, I can bring out the negative.
Okay. That's good. That's really helpful.
So constants can always be taken outside. Now, it's a little different if it's this. Now that's not the same. Now I can't take that 3 outside. But notice what I can do. I can factor the 3, leaving x minus 1. And now I can take the 3 outside.
Okay. Oh, okay. Yeah. That makes sense.
In other words, as long as it's just a pure multiplier. In this case here, this 3 is not the only thing going on. I'm subtracting 3 from that afterwards. So I can't just pull that 3 out alone.
Right, but you have to factor it.
Once I factored it, now I have the product. I have 3 times the product of that. And since that's a constant, I can bring it out. I cannot bring any of the out.
And so graphing that, let's just for practice graph that. So that would be 1 to the right. Correct. And then it would have a slope of 3 mirrored.
Correct. So I go 1 to the right, there's my vertex, and I have a slope of 3.
Okay, yeah, I definitely get that. So in this last 10 minutes, can we work on parabolas a little bit?
Sure.
He's going to give us ones that are have a lowest point and have a highest point, and I don't really get either that well.
First of all, maybe we should go over the 3 formats for parabolas.
We did that last time. I have them.
I know we did. Okay, great. Cool. So your question is how to graph parabola?
Right.
Okay. So depends on the format you get it in. If I give you this format here, a standard format,
right?
A couple of ways I could graph that. The points that you're almost always going to need to know are the vertex and the X-Intercepts.
Right.
Let's figure out the vertex. The easiest way, when you get something in standard format, the easiest way to figure out the vertex is to use this. The x-coordinate of the vertex is equal to minus b over 2a. Now, if you have any trouble memorizing that, but you know the quadratic formula, notice what this is. It is the first half of the quadratic formula.
Just a small part of
that part. So if you know either the quadratic or this, it helps memorizing the other.
Okay.
Okay? So minus b over 2a is the simplest way to get what's called the line of symmetry. In other words, wherever this parabola is, you can draw a vertical line right through its vertex.
Right. And parabolas are always equal on both sides, right?
Yes.
From the vertex?
Symmetrical, yes.
Okay, so it would be negative 7 over 2.
So now I know my line of symmetry is at minus 3.5. So I can begin to know where that parabola is. Now, I didn't get the y-coordinate of the vertex. How do I get...
Wait, how did you find out the line of symmetry?
That's the same as the x-coordinate of the vertex. In other words,
okay.
This thing either is like that, or it's like that, or it's like
somewhere.
That.
It's somewhere where the vertex is on that line.
Yes, the vertex x-coordinate is minus 3.5.
Oh, so negative 7 over 2 is negative 3.5. Okay.
Right. Now, to find out which parabola it is, I need the y-coordinate.
Okay.
How do I get the y-coordinate?
How do you get the y-coordinate?
What's y?
You plug in x.
Right, exactly.
So it would be y equals 3.2 squared, 3.5 squared.
Correct.
Plus 7 times 3.5.
Correct.
Minus 10.
Correct. Whatever that, we don't need to go through the math, but whatever that number is what I'm going to write there, and it tells me what the coordinates are. The coordinates are going to be minus 3.5, comma, whatever the y value ends up being. And so now I have the most important part of that parabola.
The vertex.
The vertex. But there's still a couple of parts missing. I don't know the y-intercepts, the x-intercepts yet. How can I figure those out? What is y when we have x-intercepts?
What is y? Wait, what?
When you're talking about x-intercepts, what's the value of y?
0.
Correct. And vice versa.
So set y equal to 0.
Yes. When you're talking y-intercepts, x is equal to 0.
Right.
So it's actually much easier to figure out the y-intercept than it is the x-intercept. But that's not really considered one of the key points. The 3 key points you always want on a parabola are the vertex and the x-intercepts.
Right, because what is, if you have the y-intercept, sometimes it doesn't even intercept y.
Exactly.
Sometimes it doesn't intercept
it always
x
intercepts y. It doesn't always intercept x.
Oh.
Okay? But even still, the y-intercept is not that valuable of a point. Who cares what that is?
Yeah, it's just 1 point.
But I really care what this is, and I always want to know x-intercepts. Okay? And you only need 3 points to define a parabola. You don't need...
The vertex and the 2 x coordinates.
That'll always... any 3 points. I could give you this point, and that point. That also defines a parabola.
Okay.
Any 3 points define a parabola. Just like any 2 points define a straight line, a linear equation.
Okay, so to find the x, we just make y equal to 0.
Correct. And now solve that.
How do you solve
the best way to solve that? Well, either factoring, in other words, this is algebra. The way you solve a quadratic is, right now we have the sum or difference of 3 items, right? Equaling 0. Cannot solve that. But if I can turn that into the product of 2 items equaling 0, then I'll know one of those has to be 0. You can't multiply 2 numbers together and get 0 unless one of them is 0.
Okay.
So I'm going to factor this. There's my product. This one is x minus 5. This one is x minus 2. Notice that, excuse me, excuse me. I have my signs all wrong here. I meant for that to be minus and that to be plus.
Right.
Okay.
Is there any way for it to be minus 10?
There is, sure. If I want to make that 11, now it's x minus 10 times x minus 1.
But wouldn't the first term be positive?
Depends on what the middle term is. Let's go ahead and make that 11, okay? Well, that's the way it factors.
Okay.
And what does that tell me my two x-intercepts are?
They are 10 and 1. So they are 10, 0, and 1, 0.
Correct. In other words, my x-intercepts are 10 and 1. Well, that also, in other words, if I started doing the problem this way instead of the other way, notice that it kind of makes it easier.
Right, if you find the x-intercepts first.
Now I have the x-coordinate of my vertex because it's got to be halfway in between. In
right.
other words, 5.
And then you just plug in for y.
Right. There is the...
So that seems like the fastest way. Set y equal to 0.
It is if it can be factored.
Right, true.
If I make that a 9 instead of a 10, now I can't factor it, and I have to use the quadratic formula. And when I use the quadratic formula, I end up with irrational answers, and then it's not always that easy to find out halfway in between.
Right.
Okay? So if the problem is given like this, I'm going to still use minus b over 2a because I can see that that doesn't factor. If the problem was given like this, well, I can see that factors. That's going to be a quicker way to get to my x-coordinate of the vertex than by using minus b over 2a. In other words, always do math in the easiest way possible.
Right.
Okay. Well, if I factor this rather than use minus b over 2a, I'm going to immediately know my x-intercepts and I'm going to know my x-coordinate of the vertex. I merely then have to plug in that x-coordinate into the equation to get my y-coordinate, and I have everything I need.
Right.
So if I have...
So it's a matter of how they give you the equation.
Yes, it is. And they won't always give it to you in standard format. They may give you it like this. Y equals 3 times x minus 2 quantity squared plus 1. Okay? Now, if they give it, this is vertex format. If they give it to you like this, well, I can immediately know my vertex. My vertex is at plus 2 plus 1. There's my vertex. Okay. And I see that that's a plus 3, so I know it opens up. So it looks something like that. And in fact, I can see right away that I don't have any x-intercepts.
How do you find out if a parabola turns downward?
If the leading coefficient is negative.
So if it was minus x.
Negative 3, then it would be a parabola that looked like that. Same vertex. But
your screen is frozen, but if it, so let's say it was minus x, that would give me a negative parabola?
Minus x squared, yes.
Minus x squared, okay.
Right. Y equal minus x squared is a parabola that just is the normal parabola reflected over the x-axis.
Okay. And you find the x-intercepts the same way?
Yeah, but here's the thing. In the original problem here, that parabola opens up, okay? There are no x-intercepts.
Right.
And what that means is that this quadratic does not have real solutions. It only has imaginary solutions.
Okay.
If you only have imaginary solutions, then you don't cross the x-axis.
Okay.
So it's possible to not have x-intercepts, but notice that not possible to not have a y-intercept.
Because it always opens.
It always is going to cross the y-axis, even if I have a parabola like that. Yeah, this will keep going in that direction,
It's not a parabola if it doesn't eventually cross
Exactly.
it. That means it's
It
not
goes
continuously
left and
growing.
right. So it's always going to cross the y-axis,
Right.
but won't always cross the x-axis. But that's very informative. If you see parabolas like that, that means there's only complex solutions.
Right. He told us that it will always cross the x-axis. So there will be 2 points that cross
Not
for all the ones he's giving us.
Not always. Only.
No, just on the test that he's giving us.
Oh, I see. Okay, good. So you won't have to deal with any complex solution.
When I get to that, I will definitely be back here.
Okay.
So yeah, okay, that helped a lot. Now I feel a lot better on all these topics.
Good.
Really quickly, I didn't write down what this formula meant, and I was staring at it earlier.
Okay.
Y minus y1 equals m times x minus x1.
That is the point-slope format for a
if you have 2 points
for a straight line. No, if you have 1 point and a slope.
Oh, right. Okay.
In other words, let's say I told you that the slope of a line is 3, and it goes through the point 2, 4. Well, there's my slope, there's my point. I can plug it directly in. What would it be?
Your slope and your point. So it would be y minus 4 equals 3 times x minus 2?
Correct. And I'm done. So you use point slope when you have a point and a slope. Well, what if I just have 2 points? What if I had that 1 point and I have another point? Well,
if you have another point, you can find the slope.
Exactly. In other words, once I find the very first job is to find the slope, and once I have the slope, I can still use slope point, and I can use either point. Once I've determined slope, then I can use.
So wait, y minus 1. So let's say you use 2, 4, and you plug in y minus 4. Your slope, your y is 4, right?
Correct.
Not minus 4.
Correct. But it's always y minus y sub 1.
Right.
So in this case, y sub 1 is this 4.
Okay.
Okay. My slope between these 2 points is actually 1. Notice. Difference in the y's is 1. Difference in the x's is 1. So 1 over 1. So I have a slope of 1, and then my x is 2.
Okay.
And the way to remember point slope is notice that if I divide both sides by this, excuse me, that should be an x1, I get this, which is rise over run. So there's really never any reason to forget what the point slope looks like.
Right.
Because it's basically the definition of slope, if you manipulate it a little bit. But there's only 1 point. And that 1 point is x1 or y1, as opposed to the way slope is defined, which is y sub 2 minus y sub 1 over x sub 2 minus x sub 1.
Right.
This is figuring out slope from 2 points. But if you have,
that makes sense.
If you already have the slope and 1 point, then you're going to use this, where there's only an x sub 1 and a y sub 1.
Okay.
All right. Can I get one last thing from you, Max, and that is your mother's email address. Is that where I should send envoices to?
Can you send it to two emails?
Sure. I have yours, if yours is what you use to sign up with.
Yeah, if you use mine, because I'll give you her email address, but she's bad with checking her email. So
it's better to send it to you?
If you send it to me, I can forward it to her and show it to her again. You know what I mean?
I'll just send it to you then.
Okay.
Okay. And, yeah, I'm presuming she's probably going to want to pay by PayPal?
Yeah, she will.
Okay. Then it's really easy. Just have her go to my digital math tutor site.
Okay. I'll tell her to go to your site and then pay.
And there's a button that says buy now. I wish the button said pay, but it says It says buy now.
Okay.
And then you won't believe how easy it is after that.
All right. Awesome.
She just has to fill in an amount and her PayPal password.
Okay. Thank you so much.
You're welcome, Max, and good luck on your tests. And if I can be of further assistance, I'm always around. So.
Okay. I'll definitely keep in contact.
Okay. Bye-bye.